Last time we introduced the concept of partial derivatives, and we saw that we define derivatives using a limit like we did in calculus 1. We are doing the differences of like essentially the rise versus run, except that now the run we do in two different directions. We do run in here, we are fixing the y coordinate and we are running on the x coordinate and then see what is the rise in the z value in that direction versus the length of the run. And in the other direction, we're fixing the x coordinate, so we're running in the y direction and looking at what is the rise versus the run. So those are called the partial derivatives, and now I have two different derivatives to look at in a function instead of just one. And there is a bunch of notations for these two functions that you will encounter at some point or another. So the most common notations are either f sub x, so that's the derivative with respect to x, the derivative with respect to y, or that's, I think, what I like the most is this. Instead of like in one variable, we used to write df dx, and when you're looking at partial derivatives, we use a different d. We use this letter, which is the letter we use for partial derivatives, just to indicate that f, whenever you see this, that is a mental reminder that f is a function of several variables, and that is a partial derivative with respect to this variable. So when I do this, I am doing the derivative that we saw where y is fixed, and I'm taking a derivative with respect to x. And when I have the subscript y, I'm doing a partial derivative with respect to y. I'm letting x be fixed and letting y run. Okay. So let's look at what those, how do you compute those, and then try to interpret them. So I'm going to start with the derivative, the partial derivative of f with respect to x. So I'm hitting, with respect to x, 4 minus x squared minus y squared. And now, since I'm taking derivatives with respect to x, the y is a constant for me, and it does not depend on x. These are two free variables, two independent variables, x and y, right now. So when I take a derivative, the derivative of 4, that's a constant, I get 0. The derivative of minus x squared is minus 2x. And the derivative of minus y squared, that's just like a 4. That's 0 again. So the partial is minus 2x. When I take the derivative, the partial derivative of f with respect to y, I'm going to take a derivative with respect to y of the same function. And now 4 is still 0. X squared is a number as far as y is concerned, so I get 0. And minus y squared, the derivative will be minus the derivative of y squared, which is 2y, so I get minus 2y. Just be careful with the signs. Okay? These are the derivative functions. These are functions that now I can evaluate at points. So they ask me to evaluate at 1, 1, and then interpret as slopes. So I'm going to do that here just numerically. If I evaluate, then what we do is you'll see this as this evaluated at 1, 1, or this evaluated at 1, 1. That means that now it's a function that I'm evaluating at a point. Why 2 coordinates? Because a derivative is still a function of several variables. Okay, it still will depend on x and y. We'll see. Right now, it looks like, oh, that's just a function of x. The y's went away. They will not always go completely away, but in this case, they did. So now I'm evaluating the function minus 2x at 1, 1, where x is 1, y is 1, so I get minus 2. And similarly, when I evaluate the derivative, the partial derivative at 1, 1, it's minus 2y evaluated at 1, 1. So I get minus 2. Now, the interpretation. So what is the interpretation here? First of all, what is the graph of this function? It is not a sphere. If it was a sphere, let me do a little bit of work before we do that. So it is not a sphere. We're looking at z equals 4 minus x squared minus y squared. If I could simplify that to x squared plus y squared plus z squared equals 4, that would be the equation of a sphere. But somehow the z doesn't have a square, so it cannot be. Paraboloid?
Yes.
Yes, yes, that is correct. So this is 4 minus x squared plus y squared. So forget about the 4 and the minus. Z equals x squared plus y squared is a paraboloid. Multiply by minus 1, and then now instead of opening up, is opening down. And plus 4, I'm raising it 4 units. So this graph is going to be like this. It's going to start at 1, 2, 3, 4 up here, and then I'm going to get a paraboloid.
What's the standard formula for
The paraboloid, the standard formula would be z equals something like x squared plus y squared, with constant in front, would like elongate it in one direction or another. That would have been a paraboloid. And now with the minus and plus 4, the transformation, it becomes something like this. Okay? The domain is everywhere. I can evaluate this at any point. So I just cut it off there, but this keeps going infinitely down. Right? When x and y are large, 4 minus those will be some very negative numbers. But the domain is everywhere. And we want to know what's happening at 1, 1. So if I go here at 1, 1, go up, well, what's the value? What's the z value at 1, 1? So the z value is 4 minus 1 squared minus 1 squared. That's 4 minus 2 is 2. So this point here, on the paraboloid, that point is the point 1, 1, 2. And the slopes are the slopes that we got, the derivatives we got minus 2 and minus 2, have to do with, first of all, I fix the y coordinate and I let it run. I'm running on the surface, but at the, I want to pass through the point. Okay, so it's this line, which is a parabola. It goes like this and it goes through the line. So because I'm running through x comma 2. So that plane is the y equals 2, and then cut it there. That's the cross section, and I'm running on that curve. And when I draw the tangent line right there, the slope of that line is minus 2. And that's the interpretation of that derivative we found that it was a minus 2. If I run in the y direction, fix x equals 2, and let y run, then what's going to happen is that it's going to look like a parabola like that, in that plane x equals 2. And there is another tangent line to that parabola, and this one in 3D also has a slope minus 2. This slope was the derivative when I run x at 1, 1. This slope was the derivative as I run in y at 1, 1. They're the same slope, but they represent the slopes of two different tangent lines at that point. Those are the two main directions, and I'm looking at how it decreases in two different directions, like this and like this. Let's look at another example. Let's find the partial derivatives of this function. So I'm going to start with the derivative with respect to x of the function. So it's the derivative with respect to x of x times the logarithm of y squared minus x. How am I going to proceed here? What rule am I using to take a derivative? It's the product rule to begin with, because it's two functions of x and the logarithm of y squared minus x. Y is a constant as far as I care right now, but there is an x inside the logarithm, so that's not just a number. So it's the product of two functions. I have to use the product rule. So I'm going to write it here. I'm using the product rule first. The derivative of x is 1 times the second function, untouched, plus x times the derivative of the second function. What's the derivative of the logarithm of y squared minus x? What rule do I need to use now? The chain rule, because that is a composition, is the logarithm with the function y squared minus x. That's like 4 minus x. I have to take a chain rule. Remember that the derivative of ln x is 1 over x, and I'm composing with y squared minus x, so it's going to be the derivative evaluated at y squared minus x, so there's going to be a y squared minus x in the denominator, times the derivative of the inside, so the derivative of y squared minus x with respect to x. Y squared, the derivative is 0, the derivative of minus x is minus 1, so I get a minus 1 on top. Okay? So the answer is the logarithm of y squared minus x. Actually, there's a minus there, so let me just write it as minus x divided by y squared minus x. And I can evaluate at 3, 2. Evaluated at 3, 2. Note that y squared minus x evaluated at 3, 2. That is 4 minus 3. That is 1. Okay, so let me write it here. That minus 3 is 1. And then the logarithm of 1 is 0. So I'm also using that the logarithm of 1 is 0 to get that this is 0 minus 3 divided by y squared minus x evaluated at 3, 2 is 1. So I just get minus 3. I'm going to try to do things less cramped from now on. So let me move on to the next slide to do the derivative with respect to y. So now I'm going to do the derivative with respect to y of the function x times ln y squared minus x. Do I need to use a product rule? X is a constant. I'm just multiplying by 7 for all I care. X is just a constant times a logarithm of a function of y. So I need to do, this is just going to be x times, it is a constant. The constant just come out of multiplying of the derivative, times the derivative of the logarithm. There I do need to use the chain rule. It's going to be 1 over x evaluated at the inside times the derivative of the inside with respect to y, which is 2y. So the answer here is 2xy divided by y squared minus x. Now evaluate at 1, 1. 1, 1, why 1, 1? I'm living in the past. 3, 2. Again, y squared minus x at 3, 2 is 1. So this is going to be 2 times 3 times 2 divided by 1. So it's 4 times 3, 12. How do I interpret these derivatives? Last time I actually showed you the graph of this function. I don't remember what it looks like. But we can interpret that one is minus 3, the other one is 12. What does that tell me? What's happening at the point 3, 2 is, first of all, what is the value at 3, 2? It's 0, so it is this point right here. It's the point 3, 2, 0. If you evaluate f at 3, 2, this is 1, so the logarithm is the whole thing is 0. Okay, so it is the point 3, 2, 0 in the graph. And what do the derivatives tell me? They tell me that if I move in the x direction, the slope of the tangent line is minus 3. So that tells me approximately that if I move 1 unit, I'm going to drop by minus 3 units. Okay, so that's just telling me that it's dropping kind of sharply in the x direction, in the positive x, which means in the negative x is growing at that rate. Okay, so that means that the tangent line looks like this in the x direction. That came out kind of crooked. And in the y direction, if I move in the positive y direction, starting from that point, the slope is 12. And that means that it's actually growing very fast in the y direction, so that the slope of the tangent line in the y direction goes up, very steep up. Okay? So that is just telling me what is happening exactly at that point, and then from that information, when the functions are very complicated, I can start sort of sketch what the entire graph could look like by knowing these slope. Let's do something that is actually a function that maybe some of you are aware. Your body mass index formula is a function of two variables. It depends on the mass, and it depends on your height. This is in kilograms and meters. So what are the partial derivatives? The derivative of the BMI with respect to mass will be, it's m times a constant, so the derivative is the constant, is 1 over h squared. The derivative of the BMI with respect to h, though, is, what is the derivative with respect to h of 1 over h squared? You can see that now, using that notation that I just erased, using primes, it's going to be very confusing. That no longer we have one variable, and I have to make sure that I know what I'm taking derivatives with respect to. So I always have to indicate that I'm doing derivatives with respect to something. So what's the derivative of 1 over h squared? What's the derivative of 1 over h squared?
Negative 2 over h cubed.
Negative 2 over h cubed. Remember that the derivative of h to the n, say with respect to h, would be n times h to the n minus 1. So the derivative with respect to h of h to the minus 2 will be minus 2 h to the minus 3, which is minus 2 divided by h cubed. So here, when I take in the derivative of the body mass index with respect to h, m is a constant, and the derivative of h squared is, so it will be 2m divided by h cubed. And I'm not going to plug in, but now you can plug in at exactly that height and that height and that this mass and this height, and it would give you what are the derivatives at that height and that mass. But what I want you to try to understand is that when I plug in here for these two numbers, I'm going to get, so after evaluation, the derivative at those values will be positive. Does that make sense? While if I evaluate at those two values, the derivative of the body mass index with respect to h at those values will be negative. That means that if I'm taking the derivative with respect to mass, if I increase my mass at a given height, my BMI will increase, right? But if I increase my height at a fixed weight, my BMI drops. That's why it's negative here, and that's why it's positive there. So you have to think about the derivatives in that sense, that I'm fixing one variable, and I want to see what happens when the other one increases, and fixing the other one, and see what happens when the other one increases. And physically, this makes sense that the body mass index would grow if your mass increases, height, same height, the body mass index drops if your height stays the same, if your mass stays the same, but the height increases. When you are growing and you're not putting mass, your body mass index drops until the pediatrician tells you to eat more. Okay. We're going to do partial derivatives of not just functions of two variables, of functions of several variables. So let's quickly calculate some partial derivatives here. So what is the derivative of f with respect to x? Now it is also a chain rule. Now y and z are constants with respect to x. So this is in some 3 dimensions, and now I can move in 3 dimensions. But here I'm only running in the x direction, and the y and the z are fixed. So this is going to be the derivative of sine, cosine, evaluated at the entire inside, times the derivative of the inside with respect to x, which is 2x. Okay? I'm not going to evaluate it, but you can just plug in the numbers if you want to see what those look like. If you do with respect to y, I'm going to get also cosine x squared plus y squared plus. And, okay, so the 3 partial derivatives look like this. Any questions about these? Higher partial derivatives. So when we did calculus 1, we saw that, yes, the first derivative tells me something about the tangent line, but the second derivative told me something about the concavity of the graph, and the third derivative and fourth derivative. They're just finer and finer information about what the graph looks like exactly at that point. So we do that here too, except that if I have a function of 2 variables, I can first look at the derivative with respect to x. That is a function of 2 variables. And now this function of 2 variables has also, I can see what happens when I grow with respect to x and what happens when I grow with respect to y. Just as I said, look at these examples. This is the partial derivative with respect to x. It's still a function of x, y, and z, right? So I can hit it again with different partial derivatives in different directions. So this one, I'm going to be able to do, for example, I'm going to be able to take the derivative of this one with respect to y. Or I could have done with respect to x. These ones, we're going to say I hit f with 2 derivatives, so a second order derivative. So we're going to write it like this. And then I'm going to indicate what was the order of derivatives. So I hit it with derivative with respect to x, and then with respect to y of that function. And this is, again, a function of 2 variables, so I could go and do it again. If I have, for example, the second derivatives of a function, I can do the second derivative with respect to x twice. This is not with respect to x squared. The notation is a little bit confusing, which also, if you want, I can call it like this. That is derivative. This one would be the derivative with respect to x and then y. Okay? So these are the derivatives that I hit derivative with respect to x, and then again with respect to x. Or I can do the one I did with respect to x and respect to y. That would be f yx. I can do xy, or I can do yy. Now I have 4 different derivatives that are the second order derivatives, and it just gets more and more complicated from there, right? So let's see just some examples. Let's find all the second partial derivatives of this function. So first, I find the first derivatives. With respect to x, this will be 4. Let's do it, right? So this is going to be 4 times 2x, 8x times y. So this is 8xy minus 3x squared. The partial with respect to y is 4x squared, 0, and then minus 2y. right? Then I'm going to do the derivative. Let's start with the xx. So take the derivative again with respect to x. That will be 8y minus 6x. Or I can do with respect to y now, and I get 8x. Here, I can do the y, and if I do with respect to y, I get minus 2. But if I hit it now with respect to x, then I get 8x. Okay? This is not a coincidence that this one and this one are actually the same. In this class, we are not going to be doing much about limits of functions of several variables, continuity, differentiability. But if the function is nice enough, the partial derivative with respect to x and then y, it actually coincides with the partial derivative with respect to y and then x. So you actually, in most cases, you only have to do one of them. Yes. So those are the higher derivatives. These are the second order derivatives. With respect to x twice, with respect to x and then y, or with respect to y twice. I am regretting my own choice that I said 2, because I think this should be that x means x and then x. And I don't want to have to switch the order. So I think it would make more sense if we call this to be the derivative with respect to x, and then I hit it with respect to y. Do you agree on that? It makes more sense? Yes. Okay, so I think this is correct. So we are going to call in that notation, in the notation with the deltas, this does mean that I'm going to hit it first with respect to y and then with respect to x. Okay? But I think it makes more sense to say that this means that I've hit f with x, which is closer to it. So I've done the x derivative and then hit it with the y derivative. So this one would be the second derivative, where I first hit with x and then and then hit it with y. I think this makes more sense of a notation. So let's keep it this way. Okay, so now what I wanted to say just briefly is that differential equations, sometimes just functions, cannot be written as a definition for the function, but many functions can be defined because they satisfy a differential equation. What that means is that the function itself is defined by a property or a relationship between its derivatives. So for example, this is the heat equation, and it tells you if you have a rod that is very hot in the middle, how over time the heat dissipates. So that is given by this differential equation. If U is the initial distribution of heat, solving this will tell you what is happening to the heat as time goes by, how it dissipates. So let me give you an example of a differential equation. Let's do that with a wave function. So this is the wave equation, and it's telling me that the second derivative with respect to t is related to the second derivative with respect to x. So let's see what happens. I'm going to start with taking a derivative of this wave function with respect to x. The derivative will be cosine of the inside times the derivative of the inside, which is just 1, so it's just this. Then that means that the second derivative with respect to x, now I'm going to take the derivative of this function with respect to x. What do I get? I get minus sine evaluated at this times the derivative of the inside, which is again 1. So that is the second derivative with respect to x. If I take the derivative of this function with respect to t, now I get the derivative of this function with respect to t will be cosine evaluated at the inside times the derivative of the inside with respect to t, and now that derivative is minus a. Okay? And now if I take another derivative of that function with respect to t, so now I'm taking a derivative of this one with respect to t, I get minus a times, the derivative of cosine is minus, so I actually get, let's do minus a times minus sine of x minus at times the derivative of the inside, which is another minus a. So if I simplify that, I get a squared times sine of, oh, there was another minus, so there's actually a minus in front, x minus a squared times the sine of x minus at. And now you see that indeed the second derivative with respect to time is the second derivative with respect to x times a squared. So it does satisfy the differential equation. Okay? And that function is indeed a wave. So this is the graph of that function. It looks like a wave, like what you would expect, but it's a wave in 2 dimensions.